We have learned that how to model the protein. Then if you don't have the protein structure, so you can just model the protein by several algorithm there you have shown in the first day. And if you have the structure F, and if the structure is not in the high quality, so you can improve the quality by modeling as well. So now you got the structure, so you want to go for the inhibitor designing. So far you can download this inhibitor, or you can just if you have some idea about how, I mean, like this chemist, they basically draw the molecules. And if you are drawing the molecules, so be careful with the geometry. So I will recommend for the do some quantum calculation of that to, I mean, improve the geometry and optimize the geometry. Then you can you know, you can just get the correct confirmation of the structure, so that you can go further for the docking or virtual screening. So for the, if you want to screen a large number of, you know, the small molecules, so you have to uh, I mean, screen it with various tool, like yesterday we have demonstrated you. And you can, you know, you perform the docking experiment several times and get the best ports. And when you have the complex, so you have like confidence that okay, this is the fine, I mean, this is the complex I want to further carry out my experiment. So you know, these complex are in statics. So in the biology, everything is in nature, everything is in dynamics. So that we want to know the dynamics behavior of this protein ligand complex. For that we are doing this MD simulation. So in the second day I have demonstrated you how to do the protein simulation. I mean, so that, you know, whenever you are going for the protein ligand simulation, so it is recommended to use also do the apoprotein simulation, so that you have something to compare with, you know, I mean, how the protein is behaving after the forming the complex, and how the apoprotein is behaving. So you have like two data to compare with. Like this experimentalist always have some data, like the wild type data and some other data. So you can compare as well in the MD simulation. So this is a really very good practice to do the apo simulation as well when you are going for the complex simulation. So without any further delay, I will start the demonstration. And okay, I'm just sharing my screen. Okay, so can you see my screen right now?
Yes.
Okay, good. So as I shown you that there is like really very nice tutorial for the GROMAX in by LAMPCOOL, so you can use that tutorial very well. But again, I am telling you that this is really very basic and just for the beginner. And I mean, this is not the optimized one, and you should not follow this tutorial blindly. So you should have some idea that what you are going to do and what exactly you want to do, so that you know, you can perform your experiment and you can perform your, I mean, redesign your parameters accordingly. Like this is not the optimal one. And also in this tutorial, like in this workshop, what I am going to I mean, show you, this is not the optimum one. So you can play with these parameters and always go to the GROMAX manual, so that you will have like broaden your idea about it. And also like in the previous session I had told you, like you should know the commands, like all the commands. Like GROMAX is really very wonderful tool that they have developed lot of command. It is like a life saving. Like in other you know, other MD simulation software, they are like so much limitation. They have not developed all the this kind of sophisticated tools or the commands, like you have to, every time if you want to do some analysis, you have to write your own script. So here it is like life saving. So maybe this is the only reason why Gromax is so popular. And also they have, like as I told you, this is not a black box, and here you can change anything, like you can redesign your parameters if you don't like yesterday I was discussing with this Chroma sports field developer. We have a like meeting, and like they have developed this SPC water model. So there are certain water model, like I can give you one working example, that there are several water models are available. So not only the force fields is not important for your getting the experimental result, reproduce the experimental result in MD simulation. The water model also really play a crucial role. Like if you are working with IDP protein, that time water model is really important. So you have to know which water model is the best for your system. And also as I told you earlier, that you should follow the benchmarking. Like whenever you are going to start your experiments, always follow some benchmarking paper, so that you have some prior idea that okay, this force field, these water models are really very great for your kind of experiment, so that from there you can have some idea. So please read the literatures and go for don't follow anyone blindly. So know your protein, know your ligands, know your project, and have some prior idea about the simulation. So before that, before performing the simulation, you should know everything. Like a small thing, like last time I told you, like the box size also play a crucial role. Like if you like some people, what they do, like they minimize the box size so that the simulation will be faster. But again, there will be some problem with the periodicity. So everything you have to know, and you have to know the theory, you have to know that because this is just like some equation, and based on the equation we are performing, and this is like completely virtual, and we have no control. So we have to use our own knowledge before going to the simulation, so that you can have some correct data, so that you can reproduce the data and compare with the experimental one. Okay, so now I assume that all the participants have some ideas. So today I will do a lot of mistake, and I want my participants that they should correct me, so that I will have some idea that okay, whatever we are demonstrating, you are learning something. So okay, so we'll solve the error. And also one participant, he sent me some error, and I didn't reply purposefully, because I wanted to show everyone that you can see, like last day I was telling you that Gromax, every time if there is some error, the Gromax is really very wonderful, that it will give some clue. So here it is clearly showing that maybe you are out of disk space. So you should check the size of your disk, like what is your disk space before running the simulation. And also I will show you how you will have some idea that how much disk space I will need before performing this this executing this command. So it will, when you are generating the TPR file, there it will give you some output, like this simulation will generate this much of data. So from that you have some prior idea, and you should clear the disk space, so that because this is like this Gromax will generate that data, and let's say you are running some microsecond simulation, and and you don't know that how much data I mean it will generate. So at that time, I mean, it is like it is not recommended to generate only one trajectory. So you should generate, multiple trajectory. You should divide the trajectory, let's say 10 nanosecond interval, and at the end you will have like different. I mean, all the trajectory you can concatenate them, and you can do your analysis. So this is another way to solve this problem, so that if this type of error will come, so that you can take a look with that. Okay, so you just submit your simulation, and you just went out and go for vacation, and when you will return, then you will get this type of error. So it's like really painful. So also this big space also really important. And as I told you, there are n number of tutorials. So, but we GROMACS people basically love this tutorial because it has a lot of description, correct description, and also like he has mentioned how, like where he did the shortcut. Like last time, one participant asked me that for the minimization, it's like 1,000. I mean, the force is like he has mentioned the cutoff, like force is should not go beyond 1,000 something. So this type of shortcut you should avoid, because he has clearly mentioned that for the the converge of the simulation, I mean the minimization, he has increased the force. So you should avoid this type of thing, because I told you, like, this is not the optimum one. So you should be careful when you are doing this simulation. Okay, so as I told you, I will do a lot of errors, so please correct me. Okay, so now we are in the working directory. So I assume that all the participant has the file which I have uploaded. So this is the protein file. If you have remember, we are working with this COVID protease protein, main protease, and for this demonstration purpose, I have took one ligands, and I have already docked it, and this is the complex one. This is the complex. If I can show you how it looks like. Okay, so this is the protein, you can see, and this is my ligand, and it's like dot complex. So this is in PDV. So before I start, like, that PDV, actually GROMACS can't read the PDV file. So for that, they have developed one command, that is GMX to, PDV to GRO. So GROMACS understand the GRO format of file. So first, what you have to do, you have to clean your PDV. As I told you, like GROMACS doesn't understand the small molecule topology. So you have to generate your topology. I mean, only some ions, only few ions, and protein, and for the protein, like the 20 amino acid parameters are inside the GROMACS. If your system has other than this atom types, so you have to parameterize from the outside of the GROMACS, and you have to generate the force field for that, and include it in your working directory. So here the ligand file is ligand file is not the parameterized inside the is not exist inside the GROMACS directory. So you have to parameterize the ligand first. So for that, you have to remove the ligand. So you have to generate another only the one file with the PDV for the protein, and also you should copy the this ligand I mean this ligand, how to say, these coordinates, and you can paste it in. I mean, I will show you how to generate this topology for different kind of force field. So you will copy from here, and you will paste in some another server. I will show you. So there are like different kind of tools you can use for different force field. If you are working with Umber, so you have to use anti-camber, or this is a Python script you can from which you can generate the topology of your small molecule. So I will show you like the Python. You have to download the Umber tool, you have to install it, and you can use it. There is one anti-camber tool from which you can generate the organic molecule, metal, etc. So actually, I don't have idea in the new version of the. I mean, this is the new version 21. I don't have an idea of how, like, what are the metals they have included. So if you are working with some noble metal, like one participant asked us, like platinum. So just check with anti-camber if they have parameterized for it. If doesn't, so you have to like make your own parameters from the experimental data, or you can use the automated Python script, that is this one. So you can use it, and but I think it also use the anti-camber. So I think you have to install the anti-camber first in your computer, then you can use this script to generate the force field.
They can install from Miniconda, I think. Yes. Just by giving on command. Yes.
Yeah. And if you are using the charm, this is the this is the server. From here you can generate the charm force field for the small molecule, and you can get the GRO and ITP file of the small molecule from here. And if you are using the Gromos one, so there are two server, that is ProDRG and ATP, and ATP is developed by our colleagues, and also there is one ProDRG, and also I have shared one tutorial for this how to use the ProDRG in my in my slide. I have already provided you. So basically you have to generate the token from here by using your email ID. So they will give you the token. So like here I got this token. So here you have to paste your coordinate. So just remember, you should, so by default it is the energy minimization is yes. So just select no, because you don't want to mess with if you minimize the energy again for the ligand, maybe it will change the conformation, and the topology file, if you'll get, maybe it will be outside of your binding sites. So please don't do, I mean, select the no here, don't do the energy minimization, and just run it. So you will get the ITP file. This is the force field parameter, and the GRO file is the Gromas version of coordinate. But the problem with this ProDRG is, the charges, whatever charges it generate is not that correct. So you have to again correct the charges from other sources, like some people use some quantum calculation like DFT and so on. So you can correct the charge, like Mulken charge you can provide here, and you can correct it. And if you are using ATB, actually you have to create one account, and here you have to go to the submit, and you will provide the net charge, and you just upload the PDF of the of your ligand, or you just paste it like here and go to the next. If the this ligand topology is existed in ATP server, they will provide you, like you can see whatever molecule topology is existed. You can also check it from here, or you can just submit, and it will just tell you that okay, this file is already exists, just download it. So from here also you can generate, get the topology, and I will show you, what is the difference, because here they already do some DFT calculation and provide you the correct charge. So if you are using ProDRG, so you have to change the charge. You can go with the charge, but that simulation, maybe the questionable, the reviewer may be asked about the charge. But here, the charge is already calculated, and you can directly use it.
Krishna, what if the cofactors included in the protein? Do you need to separate? What if the cofactors included in the protein? Do we need to?
Again, as I told you, that GROMACS is only topology for the 20 amino acid and some ions. Other than that, you have to generate like the small molecule you are generating. So anything other than 20 amino acid and some ions, everything you have to generate the topology from outside. And you can check that they have already calculated. There are several ways to calculate, like semi-empirical. This is also one lower version of quantum mechanics, and DFT, or some DFT. With Hessen, they already calculate the charge and they include in the topology file, so you don't have to care about the charge. So as per your your convenient, you can use the server. So in the ProDRG also, they don't include metal ions, but yes, here in ATP you can find some also the metal ions, the charges and in the topology, because they have calculating with quantum dynamics. So also you can, if you don't have, still the ATP is not working, and you can't getting the charge, topology, so you can directly contact these people, like you can contact Alan, he's the developer, or you can contact our colleague like Ostenbrick. They generally they have their own standalone script. You can write them, and they can provide you. If they are like busy guys, so I don't know, but you can write them. And if you are using the OPLS, so for the OPLS you can use this server. So, and also this server you can use for the OPLS, like you can generate the topology from here. So there is no boundation of the force field with the GROMACS, as I told you. Like you can use anything in GROMACS, and this is the beauty. So like here I have already generated the topology file for my ligands and the GRO file. So let's have a look. Okay, so here is as I told you, like the GROMACS GRO format is like that. This is in nanometers, and these are the parameters I have already explained you earlier, and this is the number of atoms. So just careful with that. Like here is 69 atoms. So what you will do, you will just copy everything from here to till the end, and paste it the conf gro file. So the conf gro file, how you will generate, I think you have idea, right? If any participant doesn't know how to generate a conf gro, I mean the protein to gro, I can explain it again. Okay, so nobody is saying, so I am assuming that all the participant has idea that how to generate the PDB to GRO, like if the protein PDB to the
Sir,
GRO with
can
the.
you repeat it once again?
Sorry?
Can you repeat it once again, sir?
Okay, sure.
Thank you.
I will just check okay, PDB to GRO, right? No, it is like PDB to GMX. I forget. Yeah, PDB to GMX. Actually, I use my scripts, so I already forget. So, okay, like last time I have explained you everything from here. So like you will take the PDB as an input, and it will give you the output in GRO, and you can play with everything with the flag. So by this, you can generate the GRO file, and it will give you one position distance file, one GRO file, and one topology file. So I have already explained about the topology. So as I told you, I promised you like I will do the lot of mistakes, so you have to correct me. So you will copy all the coordinate file from the ligand GRO, and you will paste it in the protein GRO file. Like here, I have tested the ligand GRO. I mean this coordinate file here. I mean below. I mean where your last PDB last coordinate is ending. So you will just add the ligand. The coordinate information. You will just paste it here, and another. Sorry. Another thing you have to update in the this GRO file is you have to you can see these are the protein coordinate. Again, you have to update this number, because as I told you, the GRO will this GRO file always have the number of atom information here. So you have to just sum the number of atom from the ligands. So you have to update it. Okay. So now my complex file is ready. So now I will care about the ITP file, means the topology file. So I will open this topology, and I will show you. So here you can see I have generated the topology from the ProDRG file, ProDRG server. So here you can see the charges of the atom. I have performed the DFT and corrected the charges and provided you. So actually I don't use ProDRG that much. I always use ATP, because as I told you, they have they have the calculate the charges with quantum mechanics. So this is like more correct. But if you can also use ProDRG and correct the charges by some another calculation. So here you can see it's like there is some atom information and also the bond and dihedral, all the and angle, all the information is there. And another thing, like some people get error here, like the atom type. Like some atom types are not compatible with the force field parameters. Like there are several versions of Chromos force field. So if you are using some other force field, then the ProDRG one, like ProDRG just generate a generalized topology for the Gromos. So basically they don't have idea about the different version. So maybe you are using some different version. So just be careful with the atom type. So you have to just change the atom type according to your the force field you are using for the protein. So basically some errors coming like DMSO, like if you have some DMSO in your ligands and something like that. So there is some mismatch. If you are getting like you will get some error like atom type is not found, something like that, you will get the error. So you have to change the atom type here in this ITP file, so that you can avoid this type of error.
Hello, Krishna. One participant asked the question that how about multiple ligands? Can we generate the single file? Can we generate the single file or multiple ITP files?
No, you have to generate multiple ITP files.
Okay, fine. Thank you. Continue.
You have to generate multiple ITP file, and you can like place it like same, like let's say there is two ligand files, so you will have two GRO file and two ITP file. So you will just paste the two GRO file in your this protein this protein GRO file, and you will include the two ITP file in the topology file. I will show you now how to include the topology, the ligand topology information in your ITP file. This top file. So this is the topology file. So here, this is the ligand topology file. You have to update here, like has include and the ITP file you have to include over here. So it will just take it as it is. And if you have two, the two topology file for the ligand, like two or multiple topology, so you can include it here as well, like the two ITP file over here. So, and also you have to update the this ligand information over here, because as I told you, like it is the information for the molecule. So it will, it's like you have one protein molecule, so this is one, and you have like one ligand molecule. So here, so if someone is working with multiple ligands, so if the this he has named it like UNK, like as I named it here, like the ligand is name is like UNK. So you can he or she can write like here two, because he or she has like two ligand information. But in our tutorial we have only one, so I have included only one. So I think it is clear.
Yes, Krishna, go ahead.
So far, if anyone have any doubts, so he or she can ask.
Yes, please, you can unmute yourself and ask the doubt. Yeah, Bharat, I think I think he has asked you, he has answered for your query, Bharat.
Okay, so shall I continue?
Yes, yes.
Okay, so now we have prepared the topology file. We have prepared topology file for our complex, and as well as topology file for our the coordinate file of our complex. So this is these are the two important thing. So here I will proceed, and I will get some error, and please correct me, and I will be really happy if someone will correct me. So you can see all the step from here. I have already provided this slide, as I told you, like just please make some bigger box so that you will avoid this periodic image the interaction between itself. So I will execute this file, this command. So this command is just for the creating the box. As I told you in the earlier session that you have to make one virtual box. So you can also play with the box type according to your protein. So here I choose box type is cubic. And as I told you, from the protein and the edge of the box distance is 1.5 nanometers. And this is the output of output which I will generate, and this is the input, like this is the coordinate file of our our complex. And using the edit conf, as I told you, you will generate the box. So I have generated the box right now outside my proteins. So now the next step is I have to solve it with the parameterized water molecule. So here I have took the SPC1. You can take anything you like. So here I'm taking the output of the previous command, that is new box GRO, and I will insert the parameterized water inside it, and this is the output, and this is my topology. So I will use this command, and solvate is the command to command for the solvation. Okay, so here I will get some error, so please correct me. Okay, so I didn't. Okay, I'll tell you this is the error I will get the next step. Okay, so now assume that our protein is, we have generated the box, and inside our box there is the parameterized water. So now the next step is insert the ions. So for that I will generate the TPR file. So I think here I will get errors. Yes. Okay, so can anyone please tell me what's the error?
Yes, please, you can unmute.
And so that maybe you can see there is error, like the number of coordinate in the coordinate file, that is our solve grow file, and the topology file is mismatched. So can anyone, and you can see the number of atoms here, and in the topology number of atoms is here. So can anyone tell me what's the error here and how we can tackle it? Okay, no problem. I will explain. So if you are getting this type of error, so always open the topology file and the GRO file. Okay, so let's open the topology file. Okay, so now you can see, when if somebody has noticed when I was explaining this ITP file, like including the ITP file over here. If someone has noticed that I have already the sol file, I mean number of solution here, and I mean previously I had included, and also the charges like the ions information here, and again I have solvated so that so that the solvate command again include some solvate some water molecule inside the box. So now the box has only this much of water molecule, but the topology file has everything. So you are getting the error. So I think it is clear to all of you. So now what you will do, you will just, this type of error basically we face in when we do the simulation. So don't worry about this error. So always go to the beginning of where you started, and you can just and from the clue also, like whatever clue GROMACS is giving us, from the clue also you can rectify it. So I will just delete it and perform this again. So always remember that your topology file is correct, and just remember, and just just read everything from the topology file. So from that you will have an idea that how the GROMACS is writing. This is just some script, like GROMACS has inbuilt script, and it is writing it like this. So this is just a script, and GROMACS doesn't understand what it is doing. Like, you are the user, and you have to understand, and you have to perform the experiment. So just careful with this type of thing. Maybe at the end you will find that you have done everything wrong. So just be careful. So again, I have updated this topology file. What are the mistakes? So I will do it again. So we will generate the box. We will generate the box again. So my box is ready. Then I will go to, again, I will solve them. So now let's open the topology file. See, here you have the water information. It is updated now. So now it is correct. And we will go for the TFR file generation for the including of the ions. So now see, there is no mistake. So it included the ions, as I told you, like I have already explained the gen ion command. This gen ion commands is like inserting of the ions in your system. So here I will choose the sol. As I told you, you will insert the ions in your box, not in your the protein. So if you will choose the protein, maybe it will just remove some of the atoms from the proteins and force the ions to get into the protein. Actually, I have never choose, so maybe you can play with it. What is happening? So here I will choose 15 because this is, and I will tell you what is, like, how you can make this type of grouping. Like, this is like the index file. I will tell you later. So here I have choose the sol, and now let's go to the topology file and check it. Like what is happening? So here, like you can see that it's already solvated with proper number of ions and neutralize the system, and also like that maintain the concentration. So now you have to perform the minimization step. So for this, you will generate this PPR file again, and you have to run your minimization. Okay, so if it will take some time, so if you have any questions, so maybe the questions are welcome.
Sir, I have a question.
Yep.
Sir, on the slide number 5, can you just please come on that slide?
Yep.
The first step when we started. Yeah, sir, I have run this into my system, but when I'm adding ions, I'm getting an error as it is not able to read or something like that. So, what would be the problem?
Actually, I mean, can you share what exactly the error? Because
So it is stating me that it's a fatal error, something
Yes,
like
okay.
that. Is
You can share the screen, Aparna.
Sir, actually, currently my system is not working.
No problem. You can
I don't have electricity.
screenshot and send it in the chat.
okay, so maybe you can
Okay.
write to me, because I
Okay,
can't, because all the errors are fatal errors, so so I can tell you.
Okay. Okay, sir. And sir, on the slide number 6, what you have shown in this, when we are equilibrating with NPT. So basically, what we are exactly creating in this NPT file?
Is like we have a lot of discussion in the earlier session, and maybe you can check the video again, and it will clear your doubt, but still I am just trying to explain you in the layman language. So here, basically, in the NBT step, you are adding the temperature, and in the NPT step, you are just adding the temperature as well as the pressure. So this is just for the equilibration. I have also given one example, like just imagine the glass of water. You want to make a perfect mixture of the water.
Yes.
So you have to stir it. So basically, we are doing the similar kind of stuff here. So it's like science is really very wonderful, and here like we are just mimicking the nature. So just imagine the simulation in that way, like you are just making one perfect mixture, like in the in the wet lab we do a lot of centrifugation for the perfect mixture, so here also just imagine it like it is a like perfect centrifugation. So
okay, yes sir, thank you. Yes sir, I'll just check the videos.
yeah, no problem. So any other question? So now we have minimized the system, and as previously we had like the same step we will follow, just little bit of changing with the temperature coupling. And also like there are several things, like I have told you, like about the position restraint, like last time we have position restraint this the protein. So here also you can position restrain your ligand, because if you don't, maybe the ligand if the ligand is not perfectly bind with the binding site, maybe it will come out, or and in the some simulation, like people complain that when they are running the MD step or equilibration step, the ligand is coming out from the binding site. So these are the same error we basically see, and sometime like the ligand is like you will assume, I mean you will realize it like end of the simulation. So please restrain your ligand as well along with your protein, and this will like help you with this type of problem. Like you can just create one position restraint file for your ligand, as I showed in the earlier video. You can see like how like how to generate the position resistance. I don't want to go it, do it again. So you can either that way you can generate the position resistance for the ligand as well, and you just include it. Okay, so our minimization is completed. I will just okay, I have, as I have promised, like I will show you how to make an index file. So if anyone have any idea like how to make and what is index file and how to make it, just not make it, like what is index file. Okay, no problem. I will explain you. Index file is just like a, you are making in like in general life, we just make index of anything. So here also Bromax make an index of all the atoms. So with this command, make ndx, if like we are taking the last the last output, the coordinate file of the EM step, and we will make an index file over here. So here you can see lot of indexing has been already done by Linux. Like the system, it has all the atoms, like the protein, it has all the atoms. So here I want to make an index, let's say protein. So for that I will choose 1, like protein is here, and let's say I will make index of my ligand. So this one, and here you can see, how to do it. Here also there is some clue, and I will choose, let's say, the ligand. So it make another one, like there was initially it was like 23 index, so it created another index, like copy the index group 1, like a protein, and it also copied the index group 20, like the ligand information, and it merged it. And in the initially it was like 3052 and 69 atoms in the ligand. So now it updated the information and created another one. Let's say I will make index of backbone, let's say 4, and I will make index of ions. So here, ions is 19, and I want to make index of 20, so like the ligand. So it make another index like 25, which having the information of backbone, ion, and the ligand. So in this way you can make a lot of like you can make a index file. Let's say you want to calculate the distance between the particular atoms. Let's say you found out that there is one catalytic catalytic residues, and this catalytic residue is having some interaction with your ligand. So you want to see what is the distance between that particular catalytic residue and your ligand in the time scale, like during the simulation, what is the distance it is maintaining. So for that you can choose the particular atoms. So like here you can choose the atoms, and you can make one atom index. And first you have to know which atom is that particular, like the atom of atom information of the hydrogen bond, so that you have 2 atom information. So you will make one atom index and again another atom index, and you can calculate the distance. So you have an idea that the hydrogen bond length will not go beyond 4 angstrom during, I mean, after you, if you will stretch it, so it will not go beyond 4 angstrom. So if during the simulation, if this atom distance is go beyond 4 angstrom, so you can say that, okay, this atom is, I mean, in certain time scale, it is not forming the hydrogen bond. So from that also you can have some valuable information about your simulation. So in this way, you can generate a lot of information. And also, like, let's say some there is some salt bridges. So you want to know the, I mean, the salt bridges is existing during the simulation or not. So in this way, you can calculate it. So you have to save it. So for the saving, you will write Q and enter. So you will have generate one index file, updated index file. If I will open, you can see the system having all the atom information, whatever inside your this system. So as we created the backbone ion and UNK, like the ligand, you can see the backbone atom information of the protein. Then I think this is the protein. This is the ligand or ions, and your UNK. I mean from here, this is, I mean from, yeah, this is like the last one is the ligand atom information, and this one is the protein atom information. So like protein and UNK. So now we will run the NVT step and NPT step, and like as before, we have already performed it in the previous session. So I will just check the MDP file again. Okay, so for the tutorial purpose, I will just run it like 2 seconds, because this is I mean, we can't wait whole day. So I will just run it right here. So again, I just want to tell you, like, this is the position restraint. Here you can control this position restraint information. So you have to include, if you generated one position restraint for ligand, you have to include it here as well. Here. And, okay. Okay, so now you can also include the updated position, I mean the index file information using -n and index. So it will take the index file. So we have generated the ITP file. So now we will run it. It will just run it for the 10 picoseconds. So just for the demonstration purpose, but don't do it for your research. Just run it a little bit faster. And as I told you earlier, that you should I mean, generate multiple MDP file with different position restraint and different temperatures, so that you can gradually increase the temperature, so that your system will not get a sudden shock, and it should not collapse. So just be careful with this, and it will take some time. So if you have any questions, so it will take you can see the time also. You can see like how long it will take, and also I have promised I will show you like how much data it will generate. So here you can see when you are running the this TPR command, I mean, to generate the TPR command. So here you can see roughly it will generate 41 MB. So from here also you can get an idea that okay, my command will generate, this MD run will generate this much of data, so I should have the memory. So if you want to check the memory, I can tell you, like, there is one command that is df minus h. So here you can see the memory. So here H is not the help. Here H is the human readable form. Like if you just type df, it will give you some this type of information. So it is not that much understandable. So always use H, so that it will give you like I have, like, in this disk I have like only available 2.9 GB. Here I have like available 2.51 GB. So here also it will tell you the disk size, how much you have used, and the availability and the capacity. So that you can choose the in which disk I will store my data. And also that another tips is, if you are running your simulation in the server, like we always do, we don't run in the local machine. So always try to run in the temp folder or in the scratch folder, because and just ask your admin of the server that how frequently they delete the temp and scratch. So you should not store your simulation information inside the scratch for the long time, because they generally delete it time to time. So just ask them how frequently they delete it, so that it will just uh, just avoid. You should not store your all the information in the home directory of the of your um, server, because home directory is just a gateway to enter to the server. So you should not consume it, and maybe your server will crash. So always try to run it in the scratch or in the temp. And it is also a good practice to know, because you are running in the server, and there is some base, so PBS script, or the some sort of script basically the server use to run the simulation. So this is a good practice to make a optimum script, so that the script will send your job to the particular node. So you will copy all your file to particular node. This in the running node, where you will run your job, so that just imagine your all file in the home directory, and you are running the job in the running node, like compute node. So the problem will, every time the GROMACS will have to copy everything through there, and again you have to, and the output, like each step the output will come to the home directory. So it will just slow down your simulation. So you should write a script that all file will copy to the compute node, and it will just run it in the compute node, and when it will finish, it will copy again to your working directory, so that in that way you can foster your simulation. So there are several ways you can foster the simulation. Just you just get your hand dirty, so you can know that. So our NVT step is done, and now we will run the NPT. So here you can say that, okay, this is like 41 MB data it will generate. So as I told you, like this is a really very good practice to, copy all the information and store it for the future, because you may need it. And that time if reviewer will ask this type of information, and if you don't have, then it's not, this is not a good idea. And so I have already described everything to you. So again, we will just run the final simulation, and we will go for the analysis. So far, if anyone have any doubts, so yes, you can ask me. Okay, so another tips that you can install your GrowMax with MPI, so that you can use the multi-thread. You can define your how many number of processor you want to use. And another tips is if you have the GPU, so just install it with GPU. And by default, GrowMax is single precision, like it installing the single precision. So that's why it is really faster. Like you can also control your precision if you want more correct result. You can install it with double precision, but the thing is the simulation will be very slow. So if you run the simulation in the double precision, but that will be more accurate one. So these are the two or three tips I want to give you, and feel free to ask anything if you have. And if you have some personalized problems, so you can just write me or Rohit or Pratibda, so we'll be happy to solve. Or if you want to collaborate with us, you can anytime you can collaborate. And I must tell you that our lab is one of the best lab for the structural biology. We have almost all the facility, like we have NMR up to 950 megahertz, and we have like cryo-electron microscope, like we have like 5 cryo-electron microscope with including Titan cryos. I basically work with that, and I must tell you that Titan cryos is the best cryo-electron microscope in the world. And if you want to have like how it's called, like there is tomography. For tomography also we have facility, like you can cut your complete cell, and if you want to have a look how the cellular cell is look like, and how the protein is inside your cell, so we can cut the cell outer membrane, and we can visualize it as it is, like in the cellular condition. And also we have time frame, like you can also capture the 3D code, the 3D image, how it's called, like the micrographs, sorry. The micrographs you can like in the time frame, so that you can, like here in the simulation also we generate the time frame information, and also Cryon also we can freeze the sample in different gradient, and we can generate some movie, so you have idea that the motion of the protein you can also frame it, but it's really very tricky, so you can use it. And also we have biosats and also crystallography unit, and so we will be happy to collaborate if anyone want. And we have like very super fast supercomputer, and we have a lot of computational support, and all the developer, like the Romos developer, we have very friendly with us, and we are happy to collaborate, and happy to do some science.
Hello. I wanted to know where is this information regarding the email ID of all the speakers is given. I couldn't locate it.
Maybe the organizer can tell you, but my information is here, so you can find.
Okay, okay. Thank you.
Okay, so the NPT is done. So now we will run the MD. So we have generated the topology for the MD run. So here you can see it will generate 11 MB data. So just run it. And I can just sit. That's some mistake. And as I told you, like you have to remove the periodic boundary information from your trajectory. So because here you will get the raw trajectory. So please save it, never delete it. So again, from there you can have the PVC removed trajectory so that you will remove all the unwanted they called it like jump or something else. So you can remove that so that you will have a smooth trajectory. And I have already demonstrated you how to do all the analysis. Like there is the new analysis. Maybe I can show you that how to calculate the hydrogen bond. And from the hydrogen bond information, you can calculate the occupancy of that. I mean this hydrogen, like hydrogen bond, like the occupancy will help you to know. Okay, so from the hydrogen bond, I mean the H bond, it will calculate the this number of hydrogen bond is forming during the simulation with that time scale. So from there you will not have the idea like what are the what are the these atoms they are forming the hydrogen bond. So you can write your own script for that because the GROMACS doesn't have that. So you can write your own script and you can extract which atoms are forming the hydrogen bond, and you can calculate their occupancy. That occupancy will tell you, okay, how strong is the hydrogen bonds. And also there are several number of analysis. You can find any paper for the protein ligand information. So as I told you earlier that the binding energy which you are calculating from the docking is not the true binding energy. I will tell, because this is the scoring function based binding energy. And the scoring function is not including the water information, I mean the environment information, which is really very crucial for protein ligand. So that binding energy is not correct. Someone should not correlate with experiment. Here you can, from the simulation, you can calculate the binding energy with different tool, like there is very, popular tool is MMPBSA. From there you can calculate the binding free energy, but be careful that your tool is including the entropy information. So that there is really very interesting paper by John Zhang in the chemical review, that is SCS chemical review. They have demonstrated all the binding free energy calculation. Maybe I can show you that paper. So he has one really very wonderful review about all the binding energy. Okay, this paper. So you can go through this paper and you can have an idea about like how to, what are the drawback and what are the beauty of different, this different type of binding energy calculation they have so far. Maybe I can share with the participants. I don't know where to, maybe Abraham can share this paper to all the participants, or you can just check it, because this is recorded session, so you can just check it. This is really very wonderful paper. So from here you can have an idea about all the strategy and how to use it in the drug designing. So, but be careful that your tool is using the entropy, so that you can increase the correctly predict the binding energy. But still it is a prediction, so don't think that this is really very important calculation, because there are really very sophisticated calculation in when you are calculating the binding energy. And there is another tool called LI, GMX LI, from which you also can calculate the binding energy. So actually the thing is, these are really very quick. So you have some initial idea that okay, so these are the this is the binding energy, because when we do research, we don't do one simulation like one ligand simulation. Maybe you have 100 of ligand simulation. So at that time, what is recommended, like you should use some quick tool to screen the your correct ligand. So from there you can go, more sophisticated calculation, but SLI, MMPBSA, these are like very quick, so that quickly you can screen it. And there are another strategy of design your experiment. Like one of, actually my supervisor has one publication in back in I think in 2008 or something like that, in medicinal chemistry. What he has done, he has performed the APO simulation first. So from the APO simulation, he has generated he clustered the simulation, so that he has generated the ensemble of like the conformation of the protein. Because the docking, we don't have we cannot have the more conformation of the protein. You can generate the conformation of ligand, but not the protein. So basically you can, with the APO simulation, you can generate the conformation. So for the each conformation, you can perform the docking, and you can have an idea that you can broad your research, and you can more correctly predict the inhibitor. So the idea is not only generating the conformation of the ligand, you can also, with the simulation, you can generate the conformation of protein. So for the clustering, you can use GMX cluster command. Actually, that is a beauty, like the GROMAX, because GROMAX has so many tools you can use directly. So, and also the GMX cluster command, there are several, this type of cluster. So the quick one is the RMSD based cluster, or you can use k-mean or whatever, and you can use the cutoff, you can fit it, and there are several things you can do with it. So just play with different kind of methods. So if you want online command reference. Okay, so here you can get all the command information. Okay, whatever command is there, you can get it. So there is another one like do DSSP. This use like this is a DSSP is a tool to predict the secondary structure. So from here you can generate, get the secondary structure information of your protein during the simulation, and you can use it. You can compare with some experimental, let's say with CD, maybe from CD you can or from the chemical shift you can generate the chemicals from the chemical shift of NMR. You can generate the secondary structure propensity, and you can compare with your simulation. Let's say we will talk about J coupling. Like here, for the J coupling, you can like RDF also. One really interesting parameter you can use. You can use the order parameters and okay, this guy. So from here you can calculate the the J coupling, 300 J coupling information with almost all the the J coupling you can calculate with the GMX Sky, so you don't have to use some other these tools like or other script. You don't have to write it, so you can use it here you can see they have already the Karplus equation, so you can calculate over there. So if there is some limitation also, like some NMR group they have used the constant for the like this is the Karplus equation, they use the ABC constant. So this constant is vary from different for the different proteins, like for the IDP protein that constant is also vary, and for the for the folded they use. So just talk to your collaborator, the experimental collaborator, what they have used in their J coupling calculation, so you can also calculate the J coupling from here, and you can correlate your data. So I can show you another tool like Sparta Plus. This actually base group, they have developed a lot of NMR tools. So this Sparta server, from where you can calculate the chemical shift information from your structure. So actually the Sparta is not take whole trajectories. So what you have to do, you have to generate all the ensemble from your trajectory, like the PDBs you can extract, and for this PDB you can calculate the chemical shift, and you can average chemical shift also you can calculate from here, and you can correlate your data with the experiment. So this is really beautiful. And also one of my colleague, he has developed CD spectra, how to calculate the CD spectra prediction. Yeah, this one. You can use this tool to calculate the CD spectra as well, because there are a lot of CD spectra is coming, and actually Gabor is one of our colleague, and now he's working with Gromuller in Max Planck, and they have developed this tool. Actually, they have also developed the correct version of this tool. I mean, I think. Okay, just Google it. I don't really found it. Actually, we can use this tool for the prediction of the CD spectra from the from this simulation, and you can correlate the simulation data with the experiment one. So the idea is why we need such validation. Because if you are doing some simulation and you don't know how much correct is your data is, so from there you can predict such kind of experimental information, and you can correlate with predict the this kind of these values, and you can correlate with the experiment, and you can find the RMSD between experiment and your simulation, so that you can have an idea that, okay, I'm nothing doing anything nonsense, okay, because people are doing simulation, and they don't validate the simulation with the experiment, so that maybe these are like creating bogus paper in the in our directory, and this paper has no use, because maybe this is just junk of science. So don't do that. Always compare your experiment, your simulation with the experiment one, so that you can you can correctly say everything, like you are not doing anything nonsense. And just be careful with when you are calculating the chemical shift, because maybe you have idea about the nuclei. The different nuclei has different value, like the J, like for example, this hydrogen have a different, and for the nitrogen they have different. So just when you are doing the calculating the RMSD, so just be careful, you have properly reweight them, and you have properly use the value. So just be careful with this, this calculation, so you can predict it. So with this, we conclude my demonstration. So if someone is having any questions, so maybe feel free to ask. And I think Rohit also here, so you can give your concluding remark that for the module 1, you can also give your conclusion, or maybe Pratik can give. Thank you. Hello.
Yes, Krishna. Yes.
Yeah, so Rohit bhai, do you want anything to share?
Rohit, do you want something to share?
Some concluding remark, like what's your point of view, like when someone is doing some this type of experiment? Because Rohit is really very experienced guy. Though he's PhD, he has like more than 50 papers. It's a lot of experienced. He have, I think, more than me, so maybe he can give us some tips.
May I call Krupanidhi sir to conclude the session.
Okay.
Krupanandi sir, are you there, sir? Yeah. In your opinion, Amber or Gromax, which one is better? There is one question there.
Actually, I will not say this is really very diplomatic answer. Because you should always compare your result, because in my paper also you can see that I have compared the actually during this free time, I mean this pandemic time, I was sitting in my room and I just did some simulation, like it took me 1 week to complete, and I just compare the results. So these are the these simulation is just prediction, so it is not like the correct validation. So the paper which I have shared with you, like my paper, like recent paper, that is I'm just single author. It is like I have also compared the Umber and Gromus there. So I will not answer this question. So my answer will be like, you should compare, or you should do the simulation, and you will get to know that how much you are getting the RMSD between the experiment and your simulation. So based on that you can comment. Thank you.
Yes, thank you, Krishna. Pratik, do you have something to comment on? Dr. Pratik.
Hello.
Yeah, you're audible.
Yes. Actually, I thank all the organizers and the delegates here for taking this great initiative. And specifically speaking, this is for according to my experience till date, this was my first, lecture to a public forum, and I sincerely thank Krishnendu for that, and for specifically convincing me to do this. And then while in the course of all these lectures actually, and all these workshop sessions, so all the beginners are, it will be very easy, even if there are tutorials or other helping sources, direct hands-on experience, and literally, so detailed description regarding MD simulations or the other techniques, virtual screening and etc., docking, etc. So it will be really helpful for the beginners to deal with these problems. And obviously, eventually, these you have to delve deeper into it. While undertaking other problems, complex problems, etc. But this was really a good initiative and good effort in terms of the speakers as well as the organizers to make maybe 1 or 2 steps easier for the participants who will be working in future in this particular field.
That was so great of you, Pratik. Thank you, one and all. Thank you, especially I'm thankful to Krishnendu Bera for this wonderful session. Can I conclude? Someone has any specific doubt, you can unmute yourself. You can ask Krishnendu, because it is his last session as a speaker. Or else I can conclude the session. Yes, Krishna, we can conclude the session. If someone having any specific doubt, you can write to him. I think he has provided the email in the presentation slide, first slide. Based upon his busy schedule or some timing, he will reply to you. Okay. Most of the speakers cannot reply to you because they are in their own schedule. That's why after consulting with them only, I can share the emails to you. That's the main point. Okay. Thank you, one and all. We'll meet again. A lot more to go. You can check the schedule and what are the requirements. You can have a basic workout on what we are going to do. That's good. Anyhow, you'll find this recorded video in the Google Drive. Make good practice. Thank you, one and all. Thank you, especially Krishnendu, Pratik, and Rohit. Your team did a very great job to this module 1.
Thank you, organizer, and
Yes,
thank
yes.
you.
Kumarji
And,
sir, if you are there, you can comment on something.
if any participant has any last doubt, if he or she can ask us.
Yes. Abhishek is asking that please suggest some good resources on MD simulations.
Good resources in terms of what, like tutorial?
Resources meant he has to. I think he's a beginner. He wants to start his career in MDS.
Okay.
Yeah, I think he can do some NPTEL courses. With that, he should be aware of all the terminologies. It's a good resource to begin with. NPTEL course is a good resource.
Yeah. It's true. And also follow this. I mean, before starting your career in MDS, I will suggest that there is really very wonderful book. If you want, I can share. That is called Leech.
Yes, you can update in the Google Drive. I will share the information.
And you can find, you can just Google that PDF also available. You can just Google it.
Fine.
And the Leech. I mean, this is really very wonderful and really very easy book for understanding. And you can specially go to the chapter 4. And that chapter 4 is covering all the basic information. Actually, I also, as a beginner, because my background is not chemistry, I am from the biotechnology and bioinformatics. So my background is not the computational chemistry. So so I also, working in a really very core experimental and the core developer lab of this MDS. So as one of our speakers that they told us, like he has no background of the programming, but still he's really developing the tools. So this is like really very encouraging for us to do something like beyond of our
he's asking the name of the book which you are talking about.
Actually, the name I forgot. So can you please give me 1 minute, because I have the book. And
no problem. You can upload in the Google link.
Yeah, I think it is Molecular Modeling Principles and Applications by Leach. Maybe. Something
Leach.
Like that.
Yes.
Yeah.
Sangeeta Singh is asking, can we run more than one ligand in MD simulations?
Yeah, that is Molecular Modeling Principle and Application and Leach. So you can follow that book.
Thank you, Prathit and Krishna. I think with this note we can end this session, right?
Yeah, sure.
Yeah. Thank you so much.
Is like, can we run more than one ligand in a simulation? Is in IDOC. Sorry, it is not clear to me actually what exactly you want to know. Can we run more than one ligand? What do you mean by more ligand you want to run? Can you please...
Yeah, Sangeeta, you can speak.
Hello, sir. Yes. We can run more than one ligand. Is there any possibility with MD simulation where we can desire our ligand?
Yeah, I described you like actually one participant already asked us like he or she has multiple ligands, like 2 ligands. So you can include in the topology file as I have shown you. Maybe you just go to the the video session. So there I have already explained this thing.
Okay.
Thank you, Krishna. I'm ending the session now.
Sure.
Thank you, Prathit, Krishna, and Rohit for your extraordinary.
Thank you.